Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting first lecture for 8th week of wireless and mobile communications. In our last lecture, we talked about small scale fading and we discussed that there is an inherent randomness in wireless propagation medium. This randomness comes from the fact that there are multipath propagation in wireless environment, and further there is random variations because of relative motion between transmitter and receiver and different objects in the medium. These variations, they generally cause randomness in the received signal amplitude, phase and direction of arrival. These variations, they are observable at very short distances. For example, if we change the location for say for few centimeters, maybe you can say you can have a large difference in received signal amplitude. Or if you observe the signal for a short amount of time, say for the order of maybe seconds, in that case you observe significant amount of change in the received signal amplitude. So this was our discussion related to the small scale fading, and we started describing the channel, wireless channel. So in order to mathematically represent the channel, we use different model. First of all was the additive white Gaussian noise channel, or AWGN channel. This AWGN channel is actually a simplest form of the channel, where the received signal is actually represented as sum of this transmitted signal and the noise signal. So this transmitted and noise signal, they gets added to give a received signal amplitude. So primarily for this AWGN channel, the main phenomena which is affecting the quality of received signal is Gaussian noise, which is being added to the system, and there is no other significant phenomena which we consider for the analysis of received signal. Next model is the linear time invariant channel. So what is linear time invariant channel? As the term indicates, that this linear time invariant channel has two characteristics. First one is linear, and second one is time invariant. The linear time invariant channels is they are same as we study different linear time invariant system in other courses as well. So primarily there are two important things. This is the mathematical representation of linear time invariant channel, where we have a signal, it goes through a channel, and this channel has certain response. This HT represents the impulse response of the channel. So there are certain characteristics of channel, just like a filter. So this channel is acting like a filter, so its response is represented by its impulse response HT. So output of this part is actually as I said, this channel is behaving like a filter, so it's a simple system or LTI system. So this output will be convolution of this input, which is ST, and this impulse response. So the first part of the channel, which is encircled here, is actually represented by convolution of the signal ST and the impulse response of the channel. And second impact in the channel is the addition of noise. So noise gets added to the system. So we have certain noise which is added to the system, and the overall impact is the received signal. So basically received signal is dependent on input signal. It is dependent on the impulse response of the channel and the noise which is added to the system. As I mentioned, that noise is also random, and in certain cases HT is also random. in that case the overall receipt signal would also be random. This ST, this steric symbol represents convolution, which is defined by this integral, as we already know that this is the convolution integral. It doesn't matter whether you take ST convolved with ST or ST convolution with ST. So it's commutative. It does not matter if you change the order of the convolution. So this integral can be evaluated in this way or this way. Both results in same value. So basically this LTI system is actually represented by a channel response as well as the noise. So this channel response is that of this linear time invariant systems. So what is linear and time invariance? Let me discuss this thing. So first we start discussion on time invariance. What is time invariant channel? Time invariance means the overall characteristics of the channel. It does not change with the time. In other words, if we apply an input at certain time, of course we will get certain output, but if we delay that input with certain time duration, so we will get the same output delayed by the same amount of delay. For example, you can see that we have applied an impulse function at t equal to 0 to this ht, which is representing the channel. So this application of impulse to the channel gives an output which is represented by this impulse response here. If we apply this input, the same input but with certain delay, which is represented as tau, so we have the same input which is delayed by a certain amount of time, tau. In that case the output is still the same, so you can compare this output with this one. They are same. The only difference is that the output is delayed by the same amount of time, which is tau. So primarily what happens, if the channel is time invariant, then causing a delay in the input side will not affect the output of the system. It only delay the output. The same delay is observable in input and output side. The delay remains the same, but the shape of the output or the output signal would remain the same. So this is actually representation of time invariance, that whenever we change the time of application of the input, in that case we do not observe any change in the output side. This impulse function, you already know that it is defined by this formula. I just put it here for recalling purpose. This delta t is actually exists for only one value, which is exists for only one value, which is t equal to 0. So delta t is non-zero for only one point, which is t equal to 0, and for all other points is non-zero, is equal to 0. So it's applicable to only one point, which is t equal to 0. And the important defining property of this impulse function is that whenever we calculate area under the curve, it will give you a magnitude value of 1. So it has unit area under the curve. And second, we have a sampling property of this impulse function. If you multiply with any function, so you will get a sample of that function. Okay, second thing, what is linearity? So we discuss time invariance, and second, linearity. Whenever we refer to linearity, linearity means we are referring to two properties. One is called homogeneity and second is called additivity. Additivity means if we add two inputs, in that case the output will be sum of two outputs. So it's actually sum of two different outputs. What does homogeneity means? If we multiply the input by a certain number, so for example alpha 1, the output would get multiplied by the same number. So it's represented here. Say for example I'm considering the same function here, which is represented here. If delta t is applied to the signal and you see this response here, What if I multiply this delta t by 2? So you would get the same response, but this will be multiplied by 2. So say for example, if LTI system is here and I am multiplying, adding two inputs here, one is this one and second is this one. So these are two inputs. So the overall impulse response will be sum of outputs of these two. The first is actually output because of this one, and second is the output because of this one. And you can see that from the previous diagram we can easily estimate the output. If you understand that this is the output when you apply an same function delta t. So if we apply 2 delta t, so output will be the same ht multiplied by 2. So the first part is represented by this expression. This is ht multiplied by 2. Second part, we have delayed the output. So because it's a time invariant system as well, so the same delay is observable in the output. T0 delay is observable there. So you get the same output. You observe the same output same delay at the output T0, and because this delta t is multiplied by 3, so you see this is multiplied by 3. And third thing, the additivity, because we have applied two different impulses, that means there are two inputs, so output is sum of individual response of these two. So this is an illustration how does LTI system or linear time invariant system behaves. So it's linear because it has this homogeneity property, and additivity means if you apply sum of two inputs, so you will get the sum of the relative outputs. And if you multiply the input by a constant number, you will see that the output is also multiplied by the same constant number. So this is linearity. And from the property of time invariance, you see that the delay which is applied to the input side is reflected as the same delay in the output side. Okay, now let us move on to the discussion on a linear time variant channel. Practically, the most of the channels that we encounter in daily life, they are linear, but they are time varying. Why the channels are time varying? Because the physical environment is actually changing with time. You can consider a movement of different mobiles in the channel, because mobile equipment, they are intended to provide mobility, so they are also moving. Plus the different components of the channel, they are also moving. For example, cars, people, trees, trees blown by wind, actually they are also moving in the wireless environment. So practically the behavior of the wireless channel is actually time variant. So the more practical model is actually linear time variant channel, where the properties of the channel are also changing with time. In other words, we would say that the channel response would get changed if we change the input, if we delay the input by certain amount of time. For example, if you apply the impulse function at t equal to 0, so you would get a certain response. But if we delay the same input, is delayed by a certain amount of time, delta tau, so you would get certain output, of course, but this output would not be the delayed version of this one. You can see that the output is different than what you observed before. So the behavior, it's because the behavior of channel has changed in this period of time, tau amount of time. So in that case, the impulse response is not only function of time, but is also function of delay, how much delay you apply in the input side. So if you change the delay, you would see a different response from the channel. So mathematically, linear time and variant channel, they are also modeled in same way. This channel has certain impulse response, but there is a difference from the time variant case, that this impulse response is now function of time as well as tau. If you compare it with the previous case, for linear time invariant channel, this impulse response was only function of time, so it was independent of the delay in the input side. But for time variant channel, this impulse response is dependent on the time as well as the delay at the input side. So how much delay you observe, it will affect the properties of the channel. Plus, of course, in any case, the noise would be added to the system. So overall mathematical model for linear time variant channel would be represented in this way, that output will be convolution of ST and impulse response of time variant channel. Now this is time variant channel because this impulse response is function of time as well as the delay, and plus this noise. So this is an illustration of linear time variant channel. This channel is a more practical case because most of the wireless channel, they are time variant. Their properties, they are dependent on the delay as well. So if we change the delay, you would see that the response bit gets changed. So let us now move back to our discussion of short-term fading. We have in last week's discussion, we had a discussion on the short-term fading, which occurs because of the constructive and destructive interference between multipath waves arriving at the mobile station. Generally, this short-term fading, they are dependent on time, because with time this fading are changing. As I mentioned that practically the most common case, the most practical case for wireless channel is time varying channel, but for analysis purpose, the analysis of time invariance is relatively easier. So we start our discussion with the time invariant channel, and then we will talk about the effect of time varying channel, and we will also discuss what type of parameters would be there which represent the characteristics of time varying channels. So we start our discussion on time invariant channels. So for example, we have a time invariant channel where a base station is transmitting a signal and mobile station is receiving that signal. This ST is representing the baseband transmitted signal, and this RT is representing the baseband received signal. Because we need to modulate the signal before transmitting, so we have multiplied this ST with e raised to power j omega ct. This e raised to power j omega ct multiplication with e raised to power j omega ct represents a modulation at a carrier frequency of omega c, or fc, which is related with omega c is equal to 2 pi fc. Similarly, the same carrier frequency is observable in the received signal side as well. Okay, when the signal propagates through this wireless environment, it goes through from multiple propagation paths. So at the receiver side, you would get some of waves which are coming from different direction. You can see that some waves are coming from this reflector. There are some waves which are reflected from this one, some waves are reflected from this one, and some are reflected from this one. And at the mobile signal, you would be getting multiple copies of the overall signal which is received when they arrive the receiver from the different propagation paths. Now there are few things which need to be noticed. First of all, these different paths they may have different propagation lengths. So overall length, for example, this path, length of this path and length of this path, it would be different. So eventually, because of the different propagation lengths, the time taken from signal from this base station to the mobile station would be different. So these multiple copies of the signal they will arrive at different delays, so they are represented as delays of tau n. So each multipath component is associated with a delay. Second thing, because during propagation there is a phase change in the wave, so which depends on the propagation length as well. So this phase change would also be different for different components, because these different rays, they are coming from the different propagation paths. So eventually this phase difference which is occurring at the receiver side will be different for different types of different rays which are originated from the transmitter side. Third important thing is the amplitude, because we know that when the wave propagates in the wireless environment, there is some loss associated with that wave. So all those waves which are represented, all those rays which are shown in this diagram, they are associated with different propagation losses. So eventually each ray would experience different loss. So received amplitude, the amplitude of this received power would be different for each of the ray. So this amplitude an would be different for all the signals. So you can see that different multipath component, they arrive with different amplitudes, different phases and different delays, and all those signals, they get added to this mobile station here. So I'm having a summation here where this capital N is representing the total number of multipaths which are available, or considerable multipath number of multipaths which affect the received signal. So this overall received signal, they are represented by this expression, because each component would have certain amplitude, it would have certain delay, it would have certain phase. So all these components are there and they are added together to give an overall received signal. Plus we know that noise would be added to the system as well, so eventually the received signal would be affected by noise as well. This an is generally known as fade amplitude. This delay is actually delay of path n. This phase angle is represented as phase, and this capital N is representing the number of paths in this multipath propagation. You can see that these ans, tau n's and theta n, they are all random variable, and as well as noise nt, this one is also a random variable. These all are random variable because the wireless environment is also changing. So eventually this signal would be random, because there are multiple types of randomnesses in the received signal. This is an illustration of how would you see the wireless channel's response or impulse response of the wireless channel, because you can see that if we apply a delta function here, so if we take delta t to be this value, delta t, so eventually this impulse response would look somewhat like this, delta tn plus an, because they are having different amplitudes. So with delay tau 1 you would have an amplitude a1, with delay tau 2 you would have an amplitude of a2, with delay tau 3 you would have amplitude of a3, with delay tau 4 you would have amplitude of a4, and so on. So there are multiple copies of the transmitted signal received with different amplitudes and different delays. Okay, so you can see that there are different types of randomnesses. First one is related to this amplitude. So this amplitude, generally this one obeys the relay random distribution. We have different types of random variable, as we have previously discussed about noise, that it generally follows Gaussian distribution. Similarly, these variations, these random variables, they also follow different distributions. So this amplitude generally follows Rayleigh distribution for most of the wireless environment. The phase is actually uniformly distributed between 0 to 2 pi. So it generally follows uniform distribution. Time of arrival Tn, actually it's the distribution of time of arrival is somewhat different, because it generally depends on the nature of environment, and different types of environment they exhibit different types of time of arrival distributions. So there is no standard form of time of arrival distributions, but it can also be calculated with certain assumptions. So this is related to the randomnesses and different parameters which determine the received signals. One of the important thing that you should note that this time of arrival, because it's random variable, so it's there are different times of arrival which exist in a random variable. Generally, what happens if you observe on the longer time of arrival duration, so Tn, if Tn is larger than certain amount, so you can see that here. So generally high value of this tau n represents a longer delay. So if a signal is coming from the covering a long path, is covering a longer distance, in that case this time would be large, and because of coming from the longer path, the the wave experiences high amount of loss. So received power is generally small. So you can see that after certain time this received power is significantly small, and you can ignore the power after certain time duration. Okay, as we have mentioned that the different components of the wave, they arrive from different paths, and they exhibit different delays when propagating through the environment. So how do we characterize those delays mathematically? So what should be the parameter to represent delay? So the parameter that we use to represent delay is named as delay spread. Delay spread is actually the standard deviation of total delay. You can see that this is the formula of standard deviation, which is represented here. So this is second moment squared minus square of first moment. This tau is the delay. So if you calculate this standard deviation of all the delays in the channel, so that will be representing the delay spread. So if a channel is having small value of delay spread, in that case different components, they are having smaller standard deviation in delay. That means all the components, they are arriving with almost same time. If a channel has large delay spread, in that case there is a large standard deviation between different components, and that means the arrival of different rays, it's associated with relatively large amount of delays. So this is the mathematical representation to calculate this mean value and second moment. We multiply this delay with the relative power. A square n is actually representing the power, because an is amplitude, so a square n is power, and divide by the overall power. Similarly, tau square is actually average value of t delay square. So t square bar is actually calculated same way. The only difference is we are calculating the mean value for the time squared. So this is the parameter that we use to represent the delay in a wireless environment. this a square n is actually representing the power of the fade. Generally different components, they are received at different times, and in most cases we generally take the power samples rather than mathematically calculating the power. So we generally rely on the measurements. So those measurements, they also represent the power here. So the same formula which is based on this a square n, it can be represented in terms of the power samples as well. So these are power samples here. So P1 is the power received for first delay, P2 is the power received for second delay, P3 is the power received for third delay, and so on. And the total power would be this average value of these different samples. So you can calculate this. You can replace this a square with the power, relative power as well, to calculate the delay spread. Generally, this diagram which we have represented here, this is sometimes known as power sample profile, because it is based on the samples which we have collected from number of measurements. We conducted different measurements, and then we calculated the average amount of power, and on the basis of those average amount of power we have plotted this power sample profile. Okay, now we come to the discussion regarding the importance of calculating delay spread, because we now understand that when the signal propagates through the wireless environment, so it will reach at the receiver with different delays, and eventually the overall width of the signal or time duration of the signal would get increased because of this delay spread. So whatever symbol duration you have at the transmitter side, you would not have the same symbol duration at the receiver, because of the delay spread which is occurring because propagating through the wireless environment. So this additional delay would have a severe effect only if this additional delay is large. If the delay spread is small number, generally it has no importance if it does not degrade the performance. But if this delay spread is large number, in that case it will affect the performance of the signal. For example, if you consider the case that the symbol duration is smaller than Tn, or in other words, delay spread, the spread which is occurring in the system is larger than the symbol duration. In that case, if you transmit a symbol, like you are transmitting this symbol here, so this one represents one symbol, but of course in wireless environment you would not be sending only one symbol, so it will be a sequence of symbols that need to be transmitted. So you would transmit a symbol 1, then you would transmit another symbol, then you would transmit another symbol, and so on. So we transmit one symbol, then there is a short time gap, and then we transmit another symbol, and then we transmit another symbol. So received symbol would be somewhat like this. It would not look same as the received signal because of the delay spread. It would elongate the received signal. The problem is when this delay spread is large. Delay spread, having large delay spread means this extension, this elongation of this on time axis of this received signal will be large, and we do not have single symbol, we have symbol after one another. So first symbol would be elongated, so it occupies a larger amount of time. Second symbol would also occupy a larger amount of time. Third symbol would also occupy a larger amount of time, and so on. And you can see that the first symbol would smear into the second symbol. Similarly, second would smear into the third one, and so on. So one symbol would get smeared into the other symbols. So first symbol would interfere with the second one would interfere with the third one, and so on. So there is an additional interference because of this large amount of delay spread which we observe in the received signal when there are multiple symbols which are being transmitted through the wireless environment. So received signal would look somewhat like this, and you would see that this large amount of delay spread, it has caused an interference between two symbols which are adjacent to each other. So this phenomena is named as inter-symbol interference. I'm sorry, it should be written as ISI. This phenomena would cause inter-symbol interference, or ISI, which is illustrated in this figure here. So whenever we have large delay spread, in that case we would have an inter-symbol interference, and that symbol interference which would reduce the performance or limit the performance of the wireless system. So it is a significantly important parameter to understand how much delay spread is there in the system, so that we can avoid inter-symbol interference and we have a reliable communication established between transmitter and receiver. So far we have discussed about this multipath propagation, and we have discussed that because of the multiple arrival of rays, we generally have arrival at different times, and we get some delay in the received signal, which is measured in terms of its delay spread, or RMS value of the delay. Which is standard deviation of the delay as random variable, because it's a random variable, so we calculate the standard deviation. This delay spread is an important parameter because it gives an indication if there is inter-symbol interference or not in the wireless in the signal received from the wireless environment. On the basis of this value of delay spread, we generally characterize the channel in two categories. First one is named as flat fading channel, and second one is named as frequency selective channel, depending on whether this delay spread is smaller than or greater than this symbol duration. So we will have a detailed discussion on this flat fading channel and frequency selective channels in our next lecture, inshallah. So we stop our discussion here for today's lecture. Inshallah we will continue the same topic with focus on this flat fading and frequency selective channels. We'll continue this thing in our next class, inshallah. Okay, thank you all.